Hello. Yeah, you are audible, sir. Yeah, am I audible clearly? Okay, thank you.
Professor Lin, you can.
I'm here.
Yeah, please, you can start the session. Thank you.
Okay, thank you. So, good afternoon, everyone. I'm Lin, and I'm from NTUST. And now, due to some technical issues, so we have paper IDs 78 to the last one. So we begin at the first one, paper ID 79. The title is Data Center Networking Using Dynamic Scaling on Spring Life Architecture. So, okay. Okay.
Hello, sir.
So
can you hear me?
Okay, you can start now, right?
Yeah. Good afternoon, sir. Our paper ID is paper 79. That is data center networking using dynamic scaling on spine leaf architecture. Yeah. Shall I start?
Yeah, please. Just go ahead.
Yeah. Good afternoon, sir. I am Satish, and I am here with my team members Raju, Rahul, and Kalyan, and our team mentor Dr. G. Spurti. Before actually going into the PPT, I just want a quick intro about the project. I mean the research paper. Our research paper titled Data Center Networking Using Dynamic Scaling in Spine Leaf Architecture primarily focuses on facilitating improvements in east-west traffic within data centers. To be clear, east-west traffic refers to the network traffic that flows within the data center, in contrast to north-south traffic, which flows from data center to external networks. Traditional data centers operate on three-tier architecture consisting of three layers. They are access layer, distribution layer, and code layer. In this setup, data flows through three layers, leading to increased resource consumption and complexity in managing traffic. This problem has been addressed with the introduction of spine leaf architecture, a more efficient tool design compromising leaf switches and layer 3 spine switches. The spine leaf architecture spine leaf improvements data traffic flow and reduces resource consumption compared to traditional three-tier architecture model. While spine leaf architecture has proven to be effective, it still presents challenges such as inability of the spine switches to scale dynamically in response to fluctuating workloads and increasing traffic demands. These limitations can be result in congestion, reduced performance, and higher latency during peak periods. Our research aims to overcome this challenge by introducing dynamic scaling mechanism for the spine switches. enabling the network to adapt more efficiently to changing traffic patterns. Additionally, we provide performance metrics to evaluate the effectiveness of this approach, focusing on key parameters such as throughput, latency, fault tolerance, and energy consumption. These metrics are critical for designing a network that is not only high performing, but also scalable and resilient. Our proposed solution ensures that data center networks can handle increased demand without compromising on performance or resource efficiency. And here is the abstract of our research. As we know, the demands for data processing and storage has been growing rapidly due to cloud solutions, big data, and IoT. This has driven the need for more efficient and scalable network designs. One of the most popular architecture for modern data center is the spine leaf architecture. It is favored for its low scalability, latency, and ease of management. The spine leaf model uses central spine switches that connect to leaf switches, enabling high bandwidth, low latency, and communication within data center. However, despite its advantages, this architecture still faces challenges such as traffic congestion, resource underutilization, and fault tolerance issues. To address the challenges, we proposed a solution called dynamic spine scaling, which leverages software-defined networking to dynamically adjust to active spine switches based on real-time traffic conditions. This improves the network's adaptability by allowing it to respond to changes in traffic load during peak times. Dynamic spine scaling optimizes performance while in peak of hours. It saves energy by reducing the number of active spine switches. Our results show that DSS can reduce latency and provide energy saving during low demand periods. Moreover, it improves the throughput, fault tolerance, and overall energy efficiency in spine leaf networks. And coming to the introduction, as technologies like cloud computing, big data, and IoT evolve, networks are shifting from traditional IP-based solution to more dynamic layer 2 solutions. These dynamic layer 2 solutions enable tools and processes such as live migration under the scaling, which are essential for handling the massive volumes of data and traffic in modern data centers. For data centers to meet these demands, they must ensure high performance, scalability, and reliability. One of the most popular network architecture for achieving this is spine leaf topology. The architecture is favored for its modular design. In the spine leaf model, the spine layer connects to all leaf switches, while the leaf layers is directly connected to the end devices. However, despite of these advantages, the spine leaf architecture still faces challenges. To address these challenges, we propose a solution called dynamic spine scaling, which is a software-defined networking approach that adjusts the number of active spine switches in real time based on network traffic conditions. This dynamic adjustment ensures that the network performs optimally during peak usage periods, while also reducing energy consumption during low demand periods. Ultimately, DSS enhances the overall network performance, improving throughputs, latency, and fault tolerance. And here is our related work. Energy efficiency has become a significant concern in modern data centers. With the increasing demand for computing power, it is crucial to find ways to optimize energy usage. Research has shown that intelligent resource management and network optimization techniques can help reduce energy consumption without compromising on performance. One key approach here is real-time traffic monitoring, such as enabling dynamic scaling, ensuring that resources are used efficiently, aiding to cost saving and operational efficiency. Traditional load balancing algorithms, which were designed for static conditions, struggle with the fluctuating traffic patterns that are common in modern data centers. This can lead to issues like congestion, latency, and even service disruptions, making it essential to develop adaptive load balancing mechanism that can respond to these dynamic traffic conditions. However, overcoming the challenges of dynamic traffic management and ensuring energy requires further innovations in load balancing techniques. These solutions are critical to ensure reliability and performance in today's data-driven world. And coming to methodology of our work, we have used dynamic spine scaling, which is an innovative approach that helps overcome the limitations of existing spine leaf architecture. By using software-defined networking, DSS allows the number of active spine switches to change based on current traffic in the network. During peak periods, when the traffic is high, DSS increases the number of active spine switches to maintain optimal performances. When the traffic is low, dynamic spine scaling reduces the number of active spine switches to save energy, contributing to more sustainable data center operations. This dynamic adjustment improve the overall performance of the network while also reducing the energy consumption of switches that are not in use. To be clear, if you can see in the picture here, the switches that are being here, those are called leaf switches, and the above layer of it, they are called the spine switches. What our approach will do is that it will use software-defined networking, and it will calculate the traffic that is flowing continuously. And then based on the traffic flow, it will active or deactivate switches to save the energy. If the traffic is high, then we can activate these switches, and if the traffic is low, we can deactivate some of the switches to make it cost efficiency and energy saving. And then coming to the mechanism, and here is the mechanism. The dynamic spine scaling method adapts to real-time traffic conditions in order to optimize the number of active spine switches in a data center network. This algorithm operates by using a centralized controller that continuously monitors traffic load metrics in Mbps and system performance. Based on these metrics, the controller makes decision to either activate or deactivate spine switches based on predefined thresholds. The dynamic adaptation ensures that network maintains optimal performance while minimizing energy consumption based on current traffic conditions. And it can be mathematically expressed with this formula, that is the action equal to active if the threshold we set is greater than the traffic flowing. And then we can deactivate if the low amount of traffic is flowing through the switches. And here are the some of the performance metrics that is calculated using this DSS. First one is throughput. Throughput is defined as the quantity of information delivered to the network during its specified time. It can be measured in megabits per second by using formula. Throughput equal to data transferred by total time. That means the total amount of packets that have been delivered to a network using DSS and without DSS. And from the observations, we can see that by using DSS, we can transfer more data rather than without DSS. Without DSS, we can deliver only low amount of data. And the next metric is that latency. Latency is latency refers to the delay in the network. It is usually measured in round trip time. From this, we can see that without DSS, the average speed is very high. The average latency is very high, and with DSS, we can see that the latency is very low. This enables that, indicates that better load distribution that using DSS. And the next metric that we calculate is fault tolerance. The fault tolerance is the number of values that network can withstand in the switch. To measure fault tolerance, the number of lost packet during failure is as follows. We can calculate the packet loss with total packets sent minus the total number of packets that are being successfully received. From this, we can calculate the number of packets that is being dropped during peak time hours. And from this performance metric evaluation, we can conclude that without DSS, the packet loss has been more. With DSS, we can make the packets to flow efficiently without failure. And the final one is energy efficiency. This is one of the most important factors in the data centers. Energy efficiency is defined as the utilization of power within the network with performance. Without compromising the performance, how much energy we can efficiently use. That is, when we deactivate the unused switches, we can reduce some energy usage there. From this, we can make the energy to use more efficiently than without DSS. Here we can see without DSS, we can save more energy, and without DSS, the switches use more amount of energy, while with DSS we can make it use efficiently and effectively. And then the next one, these are all the metrics that are used to calculate the efficiency of the network using dynamic spine scaling. And then in conclusion, our research explored the integration of dynamic spine scaling in spine leaf architecture for data center networking. These findings demonstrate that DSS significantly enhance performance by ensuring optimal data flow, reducing bottlenecks, and improving network responsiveness. This approach also maintains service reliability, allowing continuous operation even during switch failures, which is critical for high demanding environments. Additionally, dynamic chain scaling contributes to environmental sustainability by reducing energy consumption, aligning with the need for greener and more efficient data center operations. As cloud computing, big data, and IoT continue to drive the demand for high-speed connectivity and efficient resource management, adaptive network solutions like DSS are essential for meeting the performance, reliability, and energy efficiency needs. And coming to the limitations and suggestions of our Web2 future, while DSS has shown promising results, there are still areas that need further investigation. Further research should focus on testing DSS under extreme load conditions and in large networks infrastructure to fully validate its effectiveness. And additionally, integrating machine learning techniques could allow DSS to predict traffic patterns and proactively manage network resources, further enhancing its performance in diverse scenarios. The machine learning algorithms can be integrated with this dynamic spine scaling so that it can expect when to activate the switch and when to deactivate the switch without the need for continuous monitoring. And then finally, thank you for attention, and we are now open to any question or feedback you may have.
Okay, thank you for your presentation. So, any questions?
Yeah, no question from our side.
Yeah. Any questions? Okay. Okay, if we do not have questions, then we move on to the next paper. Thank you.
Thank you, sir.
So the next paper is paper ID 14. So it's modified TLS protocol using BB84 protocol and bit masking. So
hello?
hello?
Yeah, hi. Is my screen visible?
Okay.
Yes. Okay. Okay. Good afternoon to one and all present here today. My name is Dithvik, and I'm here with my teammate Sanjay. And we'll be presenting our project on modifying the TLS protocol using BB8 for algorithm and bit masking. So to start off with, we'd like to provide a brief introduction on TLS. So TLS stands for Transfer Layer Security, and it's a protocol which helps ensure secure communication over the internet and over local networks as well. So TLS traditionally uses both symmetric and asymmetric cryptography, which helps ensure encryption and data integrity and authentication for transmitted data. So critical part of TLS is the key distribution algorithm. So algorithms such as RSA, Diffie-Hellman, elliptic curve Diffie-Hellman, all help in establishing a session key, which can then be further used for symmetric encryption and decryption. So the key distribution is generally performed during the handshake process. So TLS does have some well-known weaknesses, and such weaknesses include quantum algorithms such as Shor's algorithm, which can break the encryption and figure out the keys. So another well-known weakness is that it is also vulnerable to traditional side channel attacks. So now we will move to BB84. So BB84 is a quantum key distribution protocol, which helps for ensuring secure key sharing. So in BB84, we have two users, Alice and Bob. So Alice generates a random set of bits as well as a random set of bases. Bob also generates his bases. Alice then sends the photons and the state to Bob, who then receives it. Once the quantum transmission is done, we then move to a classical channel where they publicly declare their bases. So Alice declares their bases and Bob also declares their bases, and they check for if there's any mismatch or they are actually the same. If there is a mismatch, this might be due to a specific eavesdropper actually checking on the channel, because because of the no cloning principle, measuring the quantum bits actually changes the value, which then causes a mismatch. So after around q by 2, they can actually calculate the final key, which can then be used for further encryption and decryption. So as we said before, we need to reveal generally around q by 2 number of quantum bits, and this can actually lead to redundancy, as we have to discard these bits if they're found to be not equal. So for this, we have proposed our methodology of integrating the TLS protocol with BB84 algorithm, where we substitute the RSA handshake algorithm with BB84. The RSA key distribution algorithm with BB84. We will be modifying the existing BB84 protocol with K folding, as well as benchmarking the protocol through various key sizes and K values.
Thank you, Ritvik. So the K-folding algorithm came from basically the need to, like, once when two parties have shared the keys. So basically to avoid a scenario where like an attacker can basically obtain the key via like the reveal bits. So in order to prevent that, we basically have like a situation where the attacker can basically take the reveal bits and from that devise a relation between the keys and devise a relation between the bits in the reveal key. In order to prevent that situation, we basically have a scenario where we take like k consecutive bits and XOR them together like to form a mask, and that forms a new bit in the reveal key. The reason for doing this approach is that in order to generate the new key from the reveal bits, we would need k consecutive bits in order to generate the new resultant key. Doing so requires like obtaining approximately 1 by n power k probability of having 4 consecutive bits being revealed together at the same time. So as n increases, the probability of this factor would decrease as well as the k size increases exponentially. As k increases, the probability decreases exponentially as well. So as a result, an attacker being able to discover the original key would decrease exponentially, as well as able to generate the relationship between the keys is also difficult, since the relationship is now muddled with the help of a mask that helps to prevent the revealing of the original bits being transferred and hence obtaining the key. So as a result, K-folding helps to prevent those kinds of attacks. For implementation of K-folding, we basically tested it on the basic TLS architecture using Python and sockets. Furthermore, we used Qiskit to facilitate BB84 communication, as well as for encryption of the messages sent between two parties using the shared key. We used the AES algorithm for encryption. Great. So now coming on to experimental results. So we basically used the time of execution as our benchmark standard for basically checking like the time of like computational complexity of the given algorithm. So from experimental results, we find that as k size increases and for larger key sizes, the time taken to generate the keys increases exponentially. So as a result of this, there's a constraint for for hardware to decide whether to use larger k sizes or to have larger key sizes but have shorter k sizes, which might compromise security. So there is a trade-off between the choice of computational complexity versus security in this case, which has to be done through careful tuning and like adaptive, as well as adaptive hardware can basically change the value of k as per security demands. So now that brings us to the conclusion of our presentation. So basically we covered a quantum layer security, which integrates the BB84 algorithm with TLS 1.3 to address quantum computing threats. Furthermore, we have used enhancements like K-folding and bit masking to improve key security and resistance to eavesdropping. And finally, QoS bridges classical and quantum cryptography, offering integratable solutions for the future-proof communication. So the future works are that in this paper, though we focus on the transmission of messages between two parties, there still exists quantum threats towards authentication. So there could be implementation of Kyber or Dilithium-based certificates for authorization. And furthermore, we could also devise methods to protect against future sidechain attacks for quantum hardware. So as the hardware develops rapidly, we would also need to devise mechanisms to protect it against future quantum-based side-channel attacks. The QR code has the GitHub repository for the code, and everything's open source as well. Thank you. Any questions?
Okay, any questions? Okay, I have one question in page 7. I was wondering that because we see that if the key size grows, and then the time of execution time also grows exponentially. I was wondering that if the key size 32 is enough or for security, or what is the proper key size for balancing efficiency and security?
That
is
is
basically a
choice of
like
like the degree of security you want in an application. Since larger key sizes would probably imply higher degrees of security for encryption in that case. So based off the requirements in the application, so based on that we could decide the key sizes in this case. So for our experimental purposes, we tested with 64, 128, and 256 as well as 512 bits. But there's no reason why not to go with 32 bits as well. So perhaps something like embedded system applications which are heavily hardware constrained could probably go with smaller key sizes as well. But however, the choice of having k folding as well would increase the computational complexity. So this all depends on like profiling the application and deciding whether to have like appropriate key sizes or not, given like the time constraints as well as like the computational resource constraints for the given hardware.
Okay, I see. Any questions? Okay, if there's no any questions, now so we move on the next paper number 17. Okay, please go ahead. Sorry, do you open your microphone? Can you hear me? Okay.
Hello, am I audible?
Yeah. Okay.
Okay. So today I'm going to represent our team for the work like comparative study on network policy specification languages. So these days, what is being done in enterprise networking, correct implementation of various security policies are becoming increasingly difficult because of different heterogeneous organizational requirements, and these are very complex and which involves large number of data from computing devices and cyber devices. And these policies may span from resource health, configuration management, to even access control and protection against different attacks and vulnerability. And day by day, this complexity of the problem is compounded due to various reasons, like the dynamic change in the configuration of network topology, dependency between device level configurations, and other dependency like in network policies. Because of their dependency, it also sometimes leads to hidden access channel attack, which might expose the organizational resource to the attacker. So recent studies, if we see the recent status, so in recent studies shows that network policy misconfiguration leads to 60 to 80% of security vulnerability. So if we want to avoid these things, if we start manual analysis and do enforcement of security policy, it becomes so hectic because of it becomes potentially inadequate due to high potential human errors. So therefore, there is a significant need for the development of efficient policy specification language for better network policy management. So to do better policy, better network policy management, we need to see some languages using which we can really express the policy so that it will be helpful for the administrator and the policy makers, so that the conflicting policies get reduced. So here in this slide, we have shown the same status, that is, the policy needs to be very clearly specified using the language, and the language, whatever we will use, that must be uniformly representing all the network elements, like all their related elements of the network topology. So among various state-of-the-art specification languages in our work, we have focused on these three languages, specification languages, that is Ponder, OWL, and SPSL, because of their widespread use in enterprise network. So this is Ponder specification language. It means actually this language maps the security policy onto various access control implementation, like the firewall, operating system, database, all those control implementation, access control implementation we can do easily using Ponder. It basically provide four kinds of policy, like authorization, obligation, reframing, and delegation. So authorization means if we want to safeguard some resource or services against unauthorized access, and if we want to write some policy for it, Ponder actually give construct to write those policies easily. Similarly, the obligation is related to like the activities which a subject must perform with respect to the target object. Reframes is basically the actions that a subject must not perform on the target object. Means maybe if I say that on this particular machine, this particular software should not be upgraded or it should not be installed. So it's kind of reframing policies. And delegation is granting privileges temporarily for a particular set of users or group for managing the resources. And it also allow us to design composite policies like role, group, relations to define interaction between roles. And also it allow to do like it has object-oriented functionalities like policy type inheritance. So using any that object-oriented languages, we can easily implement these Ponder specification language. Similarly, there is another specification language, that is OWL language, which is basically based on the ontology, wave ontology language, and it used for semantic wave with formally defined meaning. It is basically a computational logic based language where the knowledge is expressed in OWL, and it can be exploited by computer program. And it actually provide different kind of features like classes, properties, individuals, reasoning, data values, and all these things are stored in terms of semantic web document. There are two ways we can store the data in OWL. One is XML, another is N3 notation, which is a triplet form to represent relation between entities like the first order logic. Next one is Security Policy Specification Language, SPSL. This is originally developed for implementing security policies and representing them with the use of IPsec and IKE protocol, that is Internet Key Exchange Protocol. But now after that, it also allows to express stateless and stateful packet filtering rules. So it has the features like it support general communication security policy for IPsec, and it also allow multiple distributed policy enforcement, and it also allow mechanism that facilitate policy management through authentication and authorization, and also it supports some kind of flexibility and extensibility on the language constructs. So what we did is we did an experimental setup, and based on certain policies, we took some sample policy and we tried to express those policies using these three languages. And finally, we did a comparative study that which language is more flexible to express the different policies. So this is our experimental setup where we took 5 local area networks, and all are kind of and we try to implement heterogeneous network policies. And here we have 6 lane, say it is a organizational lane, let's say, and there are some admin lane 1, administrator lane 1, administration lane 2, project lane 1, project lane 2, general lanes. There are 2 general lanes, and within each lane, like in admin and general lane, there are 2 servers, and there is a separate administrator for each of the project lane, and there is another administrator for the complete network. So these are the sample policy we have set. These are few of the policies. In the paper, we have discussed all the policies we took. This is just a sample 5 policies. We took it from the paper, our work. Some are authorization policies, some are obligation, and some are mixed of authorization and obligation. For example, first one says that project lane can only communicate with each other. There are 2 projectors lane, so they can communicate only with each other. Backup of configuration of switches, routers, firewall to be taken regularly. So it is a kind of obligation policy. And communication between general lane, admin lane should be over HTTPS and SSH, and all other service should be disabled. So these are kinds of real-time policies which are normally implemented in routers or firewalls. So, and another one is one whitelisted software can be installed. No softwares can be installed or uninstalled from project lane. In general lane, only authorized users are allowed to install or uninstall softwares. So let's see how these are implemented or expressed in Ponder language. So in Ponder language, I have expressed these languages. So just I can say one thing, like project lane can only communicate with each other. So here there are 2 policies, like this is the authorization policy. So auth plus, and this is the name of the policy. And what are the subject is the project lane. It is coming under the network and lane, and that is within the lane we have a specific project lane. And the target is also project lane. So from project lane to project lane, there is a subject and target. This is the way we write in mathematical using Ponder. And what the action is, the action basically communication of all services. So every services can be communicated between 2 project lane and vice versa. So this is actually authorization minus. That means we are not giving any other network to communicate with project lane. Similarly, there is a backup configuration of switches, router, firewall to be taken regularly. So this is another representation. Like we can say that this instruction is obligation, and it is a policy name is 2B, let's say. So it is on is the time Sunday. On this time, the subject S, which is all network devices, do a backup. So it is kind of, the representation of these policies in a abstract level or a high, you can say high level. So after this, once you implement these things or represent these policies in the Ponder specification language, then next come is your implementation scenario where you can use some other tools to really implement those policies. So these are the Ponder specification policies. You can have a look here. And this is authorization and obligation. So it is authorization minus and obligation. One policy, one part of the policy is authorization, another part of the policy is obligation. So here you are saying the patching is not allowed in project LAN. However, regular patching to be carried out in other LANs. So if as it is not allowed, so it is users in the project LAN, patching is not allowed. Basically, it is saying that thing. And in the obligation, regular patching, that is in maybe in Sunday 10 a.m. you are doing a patching on this project LAN. Network LAN minus this project LAN. So that means from the whole network, just you exclude this project LAN, and in other networks, other LANs, you do a patching. Similarly, this is another representation technique that is using OWL specification, ontology specification language. Here, before representing what we use is, there are some classes we have defined for each of the network user, policy, server, admin 1, admin 2, and each of the servers we have to give some constructs and we have to design some classes, and based on that we can represent them in terms of the OWL spec language. So for example, here in project LAN can only communicate with each other. Here we describe like policy, the name of the policy, has subject project LAN 1, has subject project LAN 2, and similarly has target is also LAN 1 and target is LAN 2. And the action we want to do is allow. So what to allow is type is actually communication. So now here we are saying that a service from S will be implemented in a in policy A. All the services are allowed. Similarly, in policy B, 1B, same thing, but only the sequence is changed, and this has subject and has target part is same for this project LAN and project LAN 2. However, here the target is admin LAN 1, admin LAN 2, because we have to discard those communication, we have to deny the communication. So therefore, the target is internet and the action is deny. So all type of communication is being denied between project LAN to other LANs, whereas between project LANs it is allowed. So that is the meaning of it. Similarly, we can see here also in the backup of the configuration of switches router. So here it is obligation. So it is on this much, event is time, has subject network devices, has action backup. So it is quite easy to represent these kind of obligation and authorization policies in OWL specification language. Here also you can see the same thing, like HTTPS and SSH is actually allowed between admin LAN and general LAN, but then other services should be disabled. So here you can see that has action is allowed between project LAN 1 and LAN 2. Similarly, from LAN 2 to LAN 1, it indicates that from if anybody want to connect from 1 to 2, he is allowed. From 2 to 1 is also allowed. Similarly, LAN 1 to LAN 2, admin LAN 1 to LAN 2 is actually denied. And another policy, similarly LAN 2 to LAN 1, it is also denied. So these are other policies we took, like software, whitelisted software should be installed, and what that in general LAN only authorized users can install or uninstall the software. So you can have a look here how it gets represented. So the basic idea is we can represent this authorization and obligation using OWL and Ponder. Now let's see the SPSL language. Here in SPSL, it is basically represent construct or objects using IP addresses. So before assuming, before writing the policies, we have given the IP address to each of the LAN and each of the machines. So for example, here you can see that the project LAN can only communicate with each other. So for LAN 1, project LAN 1, the IP address is this much, and project LAN 2, the IP network address is this much. So here we are saying that association is project LAN with the policy name P1. And what are the policies? For the destination, that means for LAN 2 and the source is LAN 1, what we do is we allow or that is export protocol, any protocol we are actually permitting, any of the protocol. That means that's why it is allowed. Similarly, from lane 1 to lane 2, it is also allowed. However, for other policies like destination except this are denied. Means for any other protocols, if the destination is either lane 1 or lane 2, any protocols gets denied. It is just the way things are written in firewall. It is similar to that. Similarly, the communication between this lane and admin lane should be over HTTPS SSH, and all other service should be disabled. So for all the policies, see this destination is this much, port number is 443, which is basically HTTPS. So we are doing a TCP permit. So it is permitting. Similarly, vice versa, we keep on writing all these things. Similarly, for deny operations, we also write the same kind of policy. We declare those policies. So, but then for other three policies, which we took as an example, that is backup of configuration switches, that is obligation, and any policies which are mixed with obligation and authorization. If obligation is there, then these things we cannot implement in security policy SPSL, because here either you can deny or allow. You cannot allow like some actions, you cannot allow actions in the sense, just like in Ponder, we can write a function that what kind of patching will be done, or kind of backup. These things we cannot do in case of SPSL. So based on that, we have compared these three languages, Ponder, OWL, and SPSL, and we have concluded that in SPSL, only authorization policy you can implement only authorized policy. However, in OWL and Ponder, almost all policy you can implement. Only in Ponder you cannot support, it doesn't support change. Change in the sense, if currently you are already implemented one policy and then you want to modify a bit of all these modify the policy constraints, then it is quite difficult in Ponder. However, in OWL it is easily you can modify the already existing policies. However, SPSL is scalable, you can scale it, but it only works with IP address and authorization policies. So as a conclusion, as we know that policy space business language plays an important role in representing network policies that must be understandable by the network administrator or policymakers, as well as enforceable in the network elements. So in this work, we presented a set of sample network policies in an enterprise network, and with the state-of-the-art policy specific language such as Ponder, OWL, and SPSL. And we presented a comparative analysis of the effectiveness and expressiveness of each policy language based on their representation. So this comparative study in turn enable the administrator and policymakers to choose appropriate policy specific language depending on the complexity of the implementation scenario. So once you represent all these things using this specification language, thereafter you can choose other tools to really implement in the or enforce in those rules in the network, like using Z3 tool or something else. So these are the references I took from. Thank you. So I will welcome any questions if you have.
Okay, any questions, everyone? Okay. Okay, if we don't have questions, then we move on the next paper. Paper ID 10.
Hi, can you see my screen?
Hi.
Hi. Can you see my screen?
Yeah, we can see your screen. Please share your
All right.
folder, please.
Yeah, I have shared my presentation slide. You can see that.
Okay. Yes,
Yeah.
yes, we can
All
see
right.
that.
Thanks. Hello everyone. Good afternoon. I am Ajhar Ahmed Ifat and I am presenting our work BiLSTM VHP, BiLSTM powered network for viral host prediction. So these are my outline of the presentation slide. We have at first introduction, then the related works, our key contributions, methodology, part of the different sections of the methodology, and finally the results and then conclusions. So we we live in an environment where both humans and different kind of animals exist all together, and these animals all often contains different kind of zoonotic viruses that they can transmit to us human when we come into contact with them. Due to their evolvability, transmissibility, and lack of therapeutic options, these zoonotic viruses often cause pandemics and havoc, such as we have seen coronavirus few years back, and then swine flu virus and other pandemics that have caused enormous loss of life. So due to this, we thought that what if we could promptly identify and isolate the origin host of those viruses so that we can uh, prevent any outbreak or at least minimize the loss of life when these viruses starts spreading. So for that reason, we at first looked into some similar works, like what works has been there done in the literature. We have seen that there are works using traditional machine learning models like SVM, random forest, and other traditional ML model to identify the origin host of influenza A virus, coronavirus, and other viruses. We have also seen that DNA or deep neural network based architectures have also been used to predict this viral host from their nucleotide sequences or other uh, features like this. So, but we found like the research gap there is that most of the works that have been done in literature, they are only focused on few common viruses like influenza A or the novel viruses that comes new like coronavirus. So but there are other zoonotic viruses like rotavirus A or hantavirus which can also cause havoc at any time. So but no one is looking into those viruses. So for that reason, we wanted to address those issues through our work. So in this work, these are our key contributions. So we introduced three curated dataset containing the nucleotide sequences for rotavirus A, rabies lyssavirus, and orthohantavirus, along with their respective host informations. Additionally, we also introduced a lightweight bidirectional long short-term memory-based model to predict the origin host of these viruses from their nucleotide sequences. And to the best of our knowledge, our work is the first to predict the host for orthohantavirus from nucleotide sequences. Additionally, our proposed model also outperform existing works for predicting the origin host for rotavirus A and rabies lyssavirus, and also our studies includes the latest sequences and also more sequences compared to the existing works. So if we talk about the methodology of this work, so we can divide them into four specific part. One is the dataset curation, then we have dataset pre-processing, and after that we have model creation and training process, and finally the evaluation of our proposed architecture. So if I talk about the dataset curation, then we curated these three dataset containing nucleotide sequences and host details of orthohantavirus, rabies, lyssavirus, and rotavirus A from NCBI virus database. And also while curating these sequences, we only kept the host that had at least 100 sequences. So the host that has or that had less than or equal to 100 sequences only, we ignored those hosts, and hosts with more than 100 sequences were retained. So this table presents an overview of our tree dataset. The orthoantivirus dataset has 9 hosts with 8,575 sequences. Rabbit virus has 29 hosts with 22,052 sequences, and finally the rotavirus A dataset has 12 hosts with 95,197 sequences. After we curated our tree dataset, we go to our dataset preprocessing step, which is divided into two part. At first, we have resizing the sequence length. As we know that machine learning based algorithms, they need an standard sequence length or a standard input so that we can process all the inputs, but the nucleotide sequences we collected, they varied in different length. So for that reason, we trained our models on three different length. One is 400, and then 600, and 1000 and 1000 bases. So the 1000 base length was selected because it encompasses half of the sequences across all the data sets. However, we haven't we have not seen any significant improvement long with the increase of sequence length. So that is why we chose only 400 bases uh, length, as it performed competitively with 600 and 1000 length, and had also reduced the computational cost. So now, as the sequences had different lengths, thus to resize them in 400 bases, what we did was the sequences with longer bases were truncated to 400 base, and the sequences that had shorter base length, they were padded by repeating the original sequences until we reach 400 base. So after resizing the sequence length, the second part of the dataset preprocessing is handling and encoding the sequence characters. So in the nucleotide sequences, there are usually 4 types of characters, which are A, G, C, and T. And any unknown characters in a sequences are usually treated as N. So all the characters that were not A, G, C, T, or N were replaced with N. And once we handled those characters, we encoded them, because the machine learning models or computer, they can understand only 0 or 1, right? So that's why we encoded them in all the characters. So these are the encoded and one hot encoding for the characters. So after that, we go to our model creation and training stage. So this is our proposed BILSTM VSP architecture. So we at first have our input layer, and followed by the bidirectional LSTM layer. So the bidirectional LSTM layer has 256 units. And it is followed by a dropout layer to handle any overfitting. So we have used 0.2 as the dropout rate, and it is followed by a batch normalization layer, and finally we have 2 fully connected layer. So the first fully connected layer, dense layer, has 64 units, and the final classification layer, it has variable unit based on the class size for each dataset. So once we have our model, we trained it on each of the 3 datasets. So for that, each of the 3 datasets were initially divided into 80% training and 20% test dataset. After that, we implemented 5-fold cross validation on the training dataset on training stage, and for each training validation combination, we train the model for 200 epochs. And from these 200 epochs, we save the model weight for that had the best validation accuracy, and we use that to evaluate our model. And as I mentioned that our dataset has high class imbalance, so that to address that, we trained the model in 2 different settings. At first, we trained it without any kind of special treatment to handle the imbalance, and also after that we trained it again uh, by adding class weight to the dataset. We found that the model performs better with class weight for orthoantivirus, but for rabies lyssavirus and rotavirus A, the model was performing better without any kind of a special treatment. Our hypothesis is that as the rotavirus and rabies lyssavirus has more data and more classes, and also comparative to orthoantivirus they are more imbalanced, so that's why probably the class weight didn't perform well for them. So here we present the hyperparameters for our model. So the base size we used 128, and then the loss function we used was sparse categorical cross entropy, which is common for classification task, and the metrics was accuracy with Adam optimizer and dropout rate, as I said, 0.2. And these are and this graph it shows the training versus validation accuracy graph for 3 of the viruses during training. So now if I talk about our evaluation, so our results, so we used we have used 5 to 6 metrics to evaluate our results, which are accuracy, micro average AUC, confusion matrix, recall, precision, and F1. So in the presentation slide, we presents accuracy, micro average AUC, and confusion metrics, but the other metrics they are presented in the paper. We haven't shown them here because of the space limitations. So our model had 89.62% accuracy for orthohantavirus, 96.5% accuracy for rotavirus A, and 77.22% accuracy for rabies lyssavirus. And also you can see that the micro average AUC for each of the 3 dataset has more than 98%. That shows the model's efficiency. Now if we look into the confusion metric, so we can see that for orthohantavirus the model is learning all the classes very well, which can be seen from the confusion metrics. And when we go to rabies lyssavirus or rotavirus A, so the model is also learning all the classes for rotavirus A very well, which is in the right. But if you look into the learning of classes for rabies lyssavirus, you will see that there are some classes that the model could not learn, because you can see that those classes are white. It is our hypothesis is that it is because of the large number of classes. We had 29 classes for rabies lyssavirus, so probably because of the large number of classes, and also because of the class imbalance, because those classes has very few sequences, so that is why there is not much for them for the model to learn. So now after evaluating our model on our dataset, we also compared with the previous work. So as I said that our model was the first one to predict host for orthantavirus, and there was no previous work. So that's why we we looked into other works, and we found that okay, the Florian Mock et al. They have proposed VDOP, which has 2 different DNN based architecture that can be trained for other viruses. So we trained both of the architecture of VDOP on our orthohantavirus dataset and compared with our work, and you can see that our model outperforms both of the architecture of VDOP. Additionally, VDOP is the only work that we found that that predicts host for rotavirus A, but their work only was done only on 6 classes, whereas our work was done on 12 classes for rotavirus A. And also VDOP can also predict uh, host for rabies lyssavirus, but they do it only for 17 classes, where we did it for 29 classes. So to compare the performance, we created a subset of our test dataset and their test dataset containing only the common classes between both of the study, and then compare the performance, and you can see that our model BioSystem VHP outperforms VDOP on 3 cases, and the rest of the 1 cases we have a tie with VDOP. So to conclude, we presented a lightweight BioSystem based deep neural network that can identify viral host of rabies Lissa virus, orthohantavirus, and rotavirus A with high accuracy. We also introduced 3 curated datasets containing the nucleotide sequences and host classes for these 3 viruses, which were collected from NCBI virus database. And in future, we would like to examine the geographical distributions of this virus host and the timing of the data collections to gain deeper insight into viruses evolutions and change in the infection trends. And also we believe that what we saw that for most of the viruses, the data that we already have, they're highly imbalanced. So probably if we take measures to have a balanced data, that will be a crucial step for advancing in this field. So these are my references. Thank you, and I would like to welcome any questions.
Okay, thank you. Thank you for your presentation. So any questions? So you mentioned your data is imbalanced, right?
Yeah.
Have you shown your class distribution or something? Because I'm curious about if it is extremely imbalanced or it's
Uh,
just a little.
yeah. So we haven't shown the imbalance ratio or class ratio in our paper, but we have made the all the codes and the dataset that we curated are public, which will make public once the
Okay.
paper is published, but we have given the link in the paper so that anyone can reproduce or can look into the data.
Okay, I see. So your one of the future direction is to deal with this imbalance case, right?
Yeah.
Okay, I see. So another one is in page 8, you mentioned that there's no significant improvement with longer sequences. So you choose 400, right?
Yes, because with more sequences we need more training time and computational cost, but compared to that, the when we evaluated, so the performance difference was around 1%. So for that 1%, we thought, okay, let's just stay with the smallest one.
So have you investigated the insight of this result or?
Yeah, we investigated. So it's not like, let's say, when we compared for 400, 600, and 1000, there is no one specific lane that was performing better always. It was a combination, and the difference ratio was within 1% ratio. In some cases, for some viruses 400 was better, for some viruses 600 and 1000. So as the ratio was very small, so we stayed with 400.
Okay, thank you. Okay, any questions? Okay, let's move on the next paper. Thank you for your presentation.
Thank you.
The paper number ID is 78. Yeah, okay, please share your screen.
Hello, am I audible?
Hi. Yeah, please go ahead.
Hi everyone. So I am Dr. Aiskant Mishra. I am working currently Assistant Professor in School of Electronics Engineering, KIIT Bhubaneswar. So today I am going to present our research paper on the topic Content Aware Prioritization Scheme with Quality of Service Based Network Resource Management using Artificial Intelligence on the Edge for Next Generation Cyber Physical Systems. So this is the outline of today's presentation. To start with introduction, research objective, proposed method, system implementation, results, discussion, conclusion with future scope, followed by references. So, as we know, next generation cyber physical system as proposed is going to be interconnection of multiple devices incorporating AI and the internet as a global data network framework, facilitating with S-Cloud hybrid computational infrastructure for cyber systems over well-established IoT as proposed, and the research work proposing AI and data-driven model, a problem solver for many complex cognitive cyber-physical applications. So in majority of these IoT applications, sensor deployment scenarios, different sensor data and contents are not equally mission critical. That means some of the data will be having more information in it, some of the data will be having less information in it, depending upon the information theory or the surpriseness or the entropy in it. So in general, the current IoT based M2M machine-to-machine communication for wireless sensor network standards and protocol does require some kind of attention regarding content payload awareness. So based on the statistical significance of the amount of the information, we need to differentiate the quality of service of the data communication inside the network. So we have formulated some objective for this research by designing a data-centric cyber physical system framework with content awareness, implementation of priority class and content characteristic modeling. So deployment of artificial intelligence or machine learning like techniques for content or sensor data classification based prioritization schemes to optimize the M2M traffic as proposed, and the QoS modeling and resource allocation scheme for prioritized packet transmission based statistical significance, the sensor data or content classification. So we have proposed a system which will consider sensor data as a regular payload of a TCP/IP protocol suite for any typical cyber physical application. The sensor data accumulated over time is a time series, and we are trying to find some features based on the information gain inside the sensor data, and based on the criticality of the data, we need to help improving the quality of service of the network resource allocation for faster processing of the critical data points. So in this paper, we have proposed a content-aware prioritization scheme, which is a multi-class based traffic profiling, queuing, scheduling mechanism, which will enhance the quality of service of critical sensor data forwarding. So for proof of concept, we have used a real-time prediction of priority-based sensor data done with machine learning based models and trained and tested based on the sample or the sensor data that we have taken, temperature sensor data. So we have compared multiple classification algorithms like support vector machine, naive Bayes, artificial neural network with multi-layer perceptrons to predict the criticality of the real-time sensor data. And based on that nonlinear multivariate features, we are trying to categorize them into multiple scale of priority. And based on that, we are going to give the network resource management that we have deployed using class-based queuing mechanism and weighted round-robin scheduler in order to give varying quality of service depending upon the predicted priority of the sensor data. So as we move forward, this is the overall system architecture. What we propose, it will be facilitated with the edge cloud kind of environment, where all the data from the wireless sensor and actuator networks, a typical IoT kind of scenario, data will be collected at the edge and the machine learning will be deployed in order to classify the data into varying level of criticality based on the information or the feature existing in the sensor data. So the first step is the content dataset acquisition. Second step is statistical significance, finding the data pattern or recognition. Then based on that, we have done the classification using machine learning based algorithms. Then that content classifier, we are going to predict the real-time sensor data class. And based on the class of the priority, we are going to profile them and provide them different quality of service resources, so that depending upon the priority of the sensor data, they will be getting the appropriate kind of network resources. So critical data can be treated with a high priority. So these are the steps as we have discussed in the architecture. The content awareness, that is the learning part, that is acquisition of the data from the sensor, from the wireless sensor and actuator network in a typical IoT and cyber physical system infrastructure. Second step would be the data or the content characteristic modeling. So this will be basically a multivariate clustering based on content statistical significance, and another variable we have taken as delta, that will be the distance between two consecutive samples, which will give us some kind of anomalies. If there is some anomalies in the sensor data, that can be treated as a high priority. For an example, if you go to the next step would be, after getting the content classifications or content class, priority class, we are going to deploy the trained model to evaluate the prediction or predict the real-time sensor data based on the trained model, so that real-time sensor data can be classified into 4 different priorities, and those 4 different priorities will be dealt in a different way as far as the networking is concerned. So in the last and the fourth step, we are going to use the network quality of service modeling for resource allocation. And based on the sensor data priority that we have obtained from the machine learning based prediction, we are going to give the appropriate network resources using the CBQ. CBQ is the class-based queuing mechanism and the weighted round robin algorithm. So the fourth step is basically the networking step. So this slide shows the first step, that is the sensor data acquisition. So here we have taken the embedded system, that is the Node MCU, which is ESP32, and we have custom made this board with the sensor integrated to it. And the right side of the picture B, figure number 2B, is showing the time series temperature sensor data. And this second step is basically modeling the characteristic of the data based on the criticality of the data. So for that, we are taking one is the Gaussian probability distribution. That means the frequency of the data points that we have captured. So this is the first part, that is the content statistical significance, that is based on the normal distribution. And here we are getting the sample or the data that we have captured for 365 days. Per hour, you are getting one sample, so 24 samples per day, so 365. To total number of samples are 8,760 samples. So based on that, we have divided the frequencies and we have got the distribution. From the distribution, we'll understand what is the amount of information which is lying in that particular data point in that temperature sensor. So based on that, we have segregated them into 4 priority scales, as priority scale 1 is the highest priority, priority scale 4 is the lowest priority. And our objective is to assign different network resources based on the priority of the sensor data. So here the second parameter, as it is a multivariate feature extraction. So this is the second parameter we have considered as delta. So delta will be having the difference between 2 consecutive samples. So as we can see in the figure number 3 here, that it shows that the sample 1, sample 2, all the time series data, and how we can find the distance between the consecutive samples. So if the distance between the consecutive samples are more, that means it is a anomaly and kind of drastic change in a sensor data parameter. So that has to be treated with high priority as per the information theory is concerned. So in order to incorporate that feature into the content classification, that Gaussian curve, we have done a rule-based classification. That means if the delta range, depending upon the data, if the delta varies in a certain range, we have changed the CSS, and that is called a delta adjusted priority class. So in order to give the practical understanding of this, table number 1 shows the data. These are the priorities, as priority 1 is the highest priority, priority 4 is the lowest priority. And this is the content statistical significance. That means the bell curve. I'll just quickly go to the figure. So this is the bell curve, which is showing the frequency distribution of the temperature sensor data. So as far as the algorithm is concerned, first we are doing the data acquisition. Then we are going for the frequency distribution, and we are getting the CSS. And from the CSS, we are getting the distribution, like what will be the higher priority. So the middle data points are having lowest priority, the extreme data points are having higher priority, as obviously. And then we are going to do the delta adjustment. So delta adjustment, we are going to use the rule-based system. So here we can see that priority 1 is getting if the value is minus 4.2 to minus 0.6, so that is the extreme one. So the adjustment will be the highest, that is priority 1. So so depending upon the anomalies, or depending upon the difference between the consecutive samples, we have tried to impact that into the priority of the sensor data. So finally, D and E are giving the content. This is the content statistical significant priority class. This is the content statistical significant plus delta adjustment priority class. So this shows in this table, as per this table. And finally, based on this label data, so this is how a sample data set will look like after applying the content characteristic modeling. So we have the sample data, we have the date, we have the temperature readings, we have the content statistical significance data, then we have the delta, that means the difference between the adjacent samples, and this is the priority class based on the delta adjustment. And finally, there is a point to be noted here. If while adjusting the priority, if the value is getting less than 0, that means it is a negative, then we are going to assign that to a highest priority, that is priority 1. So that is what we have mentioned in the rule-based system. So here this system shows, this algorithm shows, if the value goes less than 0, that means a negative value, because our highest priority is 1. So in that case, we have to make it rounded off to the highest priority, that is priority 1. So based on that, we have this shows a sample. Then the step number 3 is applying the real-time sensor data classifications. So as we have got the content characteristic modeling, based on that, we are going to implement some of the classification algorithms. So here we have compared the performance of 5 different algorithms. One is the ADA-based, second one is the knife-based, third one is the support vector machine, fourth one is the multi-layer perceptron, that is the artificial neural network based, and the last one is the decision tree based random forest. And the result shows that the random forest of the decision tree based algorithm is performing the best with 93% accuracy in prediction of the priority class of the sensor data. Then the next one would be the ANN based multi-layer perceptron, followed by support vector machine, Gaussian knife ways, and then last one is the ADA-boost. So this shows the accuracy of the content classifier based on the real-time sensor data, based on the trained model. Then coming to the fourth and last step, here we are dealing with the networking part. So we have got some intelligence or inference from the sensor data. Now we have to deploy the network based on the significance of the content. So here what we are using a class-based queuing mechanism. So the highest priority data will pass to the first FIFO, first in first out buffer. And this is basically, we have 4 different classes. So based on the priority of the sensor data, we are assigning the percentage or resource percentage. So in this case, priority 1 is getting 40, priority 2 30, priority 3 is 20, and priority 4 is 10% of the network resource. So based on the weighted round robin scheduler. So here we are putting a weighted round robin scheduler, which is quite a standard. So this shows the network performance. So this we have done on the network simulator 2 NS2. And we are seeing the performance. The first graph is showing the throughput. So throughput is basically, as you can see, I have highlighted throughput is 49, 37, 25 and 12 bytes per second for priority 1 to priority 4 respectively. Similarly, the C graph, this graph shows the packet delivery ratio, which is again for the highest priority sensor data, it is coming 0.4, followed by 0.3, 0.2, 0.1 for packet delivery ratio. And when it comes to average delay or the latency, we are getting 0.6, 0.8, 1.5 and 2 milliseconds respectively for the decreasing order of priorities. Then coming to the jitter or average jitter, variable delay, we are getting 0.1, 0.01, 0.25 and 35 and 04 millisecond respectively from the decreasing order of priority. So the result very well proves that the higher the priority of the content, the better is the POS performance, because we have scheduled it like that. So sensor data, critical sensor data are getting better network performance over the non-critical sensor data. So this is quite justifiable, and based on that, more critical information can go to the cloud from the edge network as per the requirement. So finally, the discussion on the major highlights of this contribution. So the content-aware prioritized scheme proposed in this paper is the network resource management for critical payload in the IoT network for deploying AI on the edge, with proposed CAPS QoS-based network resource management using AI on the edge. Ensure that packet containing high priority sensitive data would get more network resources and hence better quality of service performance. So sensor data is classified into 4 classes here. 1 is being the highest, 4 is being the lowest, based on the criticality or the statistical significance. And priority varying network performance is facilitated with 4 classes of QoS profile, that is the class-based queuing and weighted round-robin based scheduler mechanism, to ensure that network packet carrying high priority data would have more resources and better quality of service performance in terms of throughput, latency, jitter, and packet delivery ratio. So the content-aware prioritized scheme is a self-aware method that adapts to wider variety of data. So if the data changes, the content statistical significance also changes accordingly. So the priority class also changes. So it's a completely self-aware, and it is also scalable for a more complex real-world IoT application. So we can change the IoT application based on that. Sensor data will also change. Based on that, the content characteristic will also change, and the priority will also change. So it is completely adaptive, and multivariate feature extraction will give us that adaptiveness in deployment of real-world IoT applications. So edge computing is a key for enabling this AI and machine learning based processing on the sensor data on the edge of the network. So which is we can also integrate emerging technologies like blockchain for secured and resilient next generation cyber physical system. So conclude the paper. Content-aware prioritized scheme based QoS-based network resource management for artificial intelligence on the edge provide content priority-based differential QoS performance using class-based queuing and weighted round-robin with aid of content characteristic modeling using multivariate nonlinear feature extraction. So this paper has proposed content-aware prioritized scheme for single sensor data. So here we have taken the single sensor, only temperature sensor. So scope exists for exploring variety of multi-sensor. That means multi-sensor data fusion application also can be explored in future. So that is part of a future work. And multi-sensor and multivariate analysis for feature extraction for real-world IoT application. It would be challenging and interesting in future work. And paper consider temperature data for real-world implementation. We can also go for different type of other sensor data. So these are my references. Thank you very much. Any questions, please?
Okay, thanks you for your presentation. So any questions? Any questions? I have a question to ask. So you say that you classify the sensor data into 4 classes and 4 priority. So what if sometimes there's no statistics significant data, but sometimes it bursts a lot of significant data? Have you considered this situation or?
Thank you for this question. First of all, I would like to say any data that can be modeled as a time series. So the system what we are posing here will take not only one sample data, it will take a series of data based on the particular time series. So whatever data comes, whether you can model it as a random, but still it has some kind of distribution. So no data in the world cannot be modeled. All the data time series has to be modeled in some kind of distribution. So from that distribution, we'll get the feature. So even if that distribution is a different distribution, so the feature will be different. So not an issue for prioritizing it.
I see. Okay, thanks for your explanation. And any questions? Okay, thank you for your nice presentation. So thanks for everyone attending this session. And that's all. Thank you.
Thank you, Dr. Lin, for chairing the session. We will start the next session in 2 minutes. Are you here? Have you joined? Okay, maybe the session chair will join shortly. Stay tuned. Hello. Thank you, Dr. Ashish Tripathi, for joining. Yeah, I think we are ready to start the session. Please start the session from your side. Thank you.
Thank you. Okay, so For first paper ID is paper ID 74.
Yeah, good morning, sir. Good morning, Ashish sir. Good morning, Binayak sir.
Sir, good morning. Please start your
So,
presentation.
how are you? Yeah, okay, sir. So, yeah, our paper, we're going to, I have with me my co-author, Arpit, who is really done good work, especially in the implementation part. So, I am, on my behalf, Arpit is going to present our work. Arpit, it's over to you, please. So, I'll share the test. Share this, okay? Entire screen. Okay, just a minute. So, just a minute, sir. We're sharing the screen.
Yeah, please, sir.
Is our screen visible, sir?
Yeah,
Okay, sir. It's already there. Okay, it's already there. Okay. Let's ask
Okay.
so,
Good afternoon, sirs. I am Arpit Pandey, and today I am presenting our research titled An Extended Version of Dictionary-Based Text Steganography for Secret Covering. It is collaborative effort of Alekha Kumar Mishra sir, Danish Ali Khan sir, me, Arpit Pandey, Surbhi Anand, and Arshin Newman. We are from Department of Computer Science and Engineering here at National Institute of Technology, Jamshedpur. So let's dive into the presentation. We will start with a quick look over the content that we are going to present today. Firstly, we will start with the introduction to this technography. After that, we will discuss its challenges. Then we will have some related works to it, the research gaps, and then we will walk through the proposed work, its results, and finally we will conclude this presentation with the observations and the future directions. So, firstly, what steganography is? Basically, steganography is the concept of hiding secret information within some cover media, or you can say to embed the secret information within some cover media. And it is different from encryption in a way that encryption basically converts the secret message from intelligible form to unintelligible form. But that is not the case with steganography because it only involves hiding the message within some cover media. And in the modern times, this steganography is basically combined with cryptography so as to make it more robust and secure. And for the obvious reasons, the cover should not draw much attention of eavesdropper because it can basically compromise the secrecy. And after that, some of its applications include digital water marking for copyright protection, covert communication for secure transmission of the secret message, and quantum cryptography, which basically includes the quantum mechanics, including principles such as Heisenberg's uncertainty principle, etc. Uh, Now we will discuss what are the types of the cover text. Basically, cover text is the cover medium in which the secret information is hidden or embedded. And we can have different types of cover text such as text, image, audio, and video. In the case of text, the secret message is basically embedded in the text. In the text, in image, when image is used as cover text, the secret message is embedded in the form of an image. And when it is embedded in audio, then audio is cover text, and when it is embedded in video, then video is used as a cover text. Now, as we are presenting this research based on the text based steganography, so we will discuss what are its advantages and disadvantages. So firstly we'll start with what are the advantages of the text based steganography, right? So it is basically it is lightweight, that is it can run on the systems which have constrained capacity cities too, and it uses low storage, it has wide availability, and it is easy with low bandwidth communication. Along with that, its linguistic diversity makes it more adaptable over the different regions having different language, etc. So as we all know that everything comes with its own pros and cons, so is the case with text based steganography too. as we have seen its advantages in the previous slide, now we will discuss what are the challenges it comes wrapped in. Basically, the first challenge is to improve the capacity of the cover media to basically store more of the to hide more of the secret information without altering the actual cover text. Secondly, as there was the advantage of linguistic adaptability, but this adaptability itself comes with the challenge of adaptation, because different regions have different languages, and adaptation is also a challenge out of it. Thirdly, there is this challenge of protection against pattern analysis, because if there is a let's say there is a pattern in the cover text, so that pattern is tends to be identified by the naked eyes, and that can compromise the security or secrecy of the hidden message. Thirdly, we should make sure that the algorithms that we are using should be lightweight, and so that they can run on the resource constrained environments too. And finally, these algorithms should be efficient and lossless, encoding and decoding for non-text media as cover text, so as to ensure that there is no loss in the important information of the secret information during encoding and decoding process. After that, we will walk through the literature survey that we did before arising to the final work that we have done. And here, after reading papers, we have found some of the methods that were already used. Like there was this method of zoring the secret text with the words at the end of at the start and the end of each paragraph. One method was like this. There was another method which was based on the shapes of different letters of the alphabet. There was also a method which used only zoring the least significant bits with the secret message. And there was also a method which used AES encryption of the message, followed by basically zoring it with the least significant bits. And there was this work by DETL which drawn our attention. Basically, it used a dictionary-based structure of English sentences to select cover text, and we have worked on it further in this paper. We will look in the further slides. So let's move on to the next slide. Here are some of the research gaps that were there in the dictionary-based text steganography by DETL that we have found and worked on it. Firstly, what it did was that it randomly selected the candidate ciphertext out of the pool of the suitable sentences without applying any further step, right? And secondly, it overlooked the plain text character distribution in the ciphertext. Thirdly, the thing was that it basically used the same indices as the key for the same character repeating multiple times in the plain text. Let's say there is this secret message Aravali, and it has A repeating 3 times. So what it did was that when we found a ciphertext, what it did was that it gave the key with the repeated key index for A repeating 3 times. So it was one of its shortcomings. And lastly, it required a long cover text. So we have to get over this too. And after finding these research gaps in that base work, we basically were asked to enhance this dictionary-based text steganography. So in it, what we did was that we, rather than just randomly selecting the cover text from the pool of the sentences in the dictionary, what we did was that we basically used the frequency-based method to basically select the candidate cover text, out of which finally we would select a random text out of the candidate cover text. One work was also to ensure that there is no repetition of the key indices, right, for different characters repeated in the plain text. Let's say there the example that I gave in the last slide. If there is this secret information Aravali with A repeating 3 times, for in the base work it was that for A repeating 3 times, the key index was same. But in this work we had to ensure that the key for every A occurring multiple times, we have to ensure that this is different. And thirdly, we had to ensure that this algorithm is lightweight, and lastly, it should provide a better security. So firstly, we started with building dictionary. so it was same as in the base work. So what we did was that we just we had this file containing English sentences, and as we all know that dictionary is basically a collection of key value pairs where so we had to decide what key we have to use. So we decided that if we concatenate the absent characters in a sentence, then it can be of a better use. So we traversed to the sentences. We took the absent characters in it and concatenated it and made it as its key. So if this key was already present, then we had to kind of union this sentence with that particular with the values presented that particular key corresponding to it. And if the key was absent, then we surely had to insert the new key and corresponding and the new value corresponding to it as the sentence we are in. So this is how dictionary was made. After that, we had to encode the plain text. So as we said that we rather than just randomly selecting the possible cover text, we had to use a frequency based cover text selection method. So what we did was that we basically made a candidate list, initially empty for sure, and after that what we did, we traversed through the sentences and we checked the frequency of each character in the plain text is less than or equal to the frequency of the same character in the cover text. So if in the cover text, if there is a character in the plain text, let's say, and its frequency is more or equal in the cover text as in the plain text, so it can be a suitable cover text, candidate cover text. So we had to put in the candidate list, and we did it to make sure that for if let's say there are 3 A's in Aravali and there is a candidate cover text having 4 A's, and this applies to every character present in the plain text. If this is the case, then for sure we can ensure that for every A present in Aravali, we can basically assign different indices for every A. So for every repeating character, we will be having a different key. This was our idea. And after that, what we did was that we basically randomly selected one of the ciphertext out of the candidate list that we made, and basically we gave the cover text and its corresponding key. And after that we had to decode it. So for that, what we did was we simply had this cover text and the steganographic keys. So we took out the characters corresponding to those keys, and this is how our plain text could be reversed back, and we can get that. So now discussing its computational complexities. The time complexity of building dictionary is O of n, where n is the number of English sentences in the dataset. Secondly, the encoding process time complexity was given by O of k, where k is the plain text size. And finally, decoding requires O of k times some, where k is the size of index key. Yeah. And after that, we have these graphs where this is the graph of encoding time versus plain text size, right? So here we can see that as the plain text size increases, encoding time also increases. It's because we have to traverse through every character of the plain text to encode it. So obviously,
so both are same total,
yeah.
and so that makes it
nearly,
you can see that.
That's why it increases with the plain text size. After that, we have this decoding time graph. Yeah, where what we did was that we had this cover text and key, so we had to traverse through this key and take out the character corresponding to those indices and finally give its output. And there is this encoding time comparison with the base work done by DITL. So we can here see that our encoding time is much more than that in the case of the base work by DITL. It's because they have just they have randomly selected the cover text out of the available sentences. But what we did that we basically have incorporated it with another additional method of additional check of frequency. So that's how this time complexity that's how this encoding time has increased in our case significantly. And after that, we have this decoding time comparison with DBTS, and here we can see that our decoding time is marginally less than the base work by DITL. It's because our plain cover text to plain text size ratio is smaller as compared to the base work, which we'll see in the next slide. here it is cover text to plain text size ratio, and here ours is basically less than that in the case of the DETL. So now we will discuss what were our observations and what can be the future directions. So basically our encoding time was basically higher than that in the case of the base work. Our decoding time was marginally less. Our cover text to plain text size ratio was better that in the case of the base work, which we have taken as the counterpart. In future, we plan to compare it with other algorithms and to use nonlinear approach to distribute plain text into cover text, and finally adopting the algorithm for image or video steganography, and we are working on that. And after that, here are the references that we used as papers and the enhancements in the steganography. And thank you for listening to our presentation patiently, and any questions or
Submitting meetings. Yeah. So we can take some questions later. Are we audible, sir? I hope disconnect. It's not disconnected. So are you audible, sir? Just a minute. You lost the connection? No. So am I audible? Ashish sir? Binayak sir? Come on. You lost the connection? No, sir. Connection. So sir. I will give you a call.
Yeah. Am I audible, Alex sir?
Yes, sir. Yes. Sir.
Alex,
Yeah,
am I
yes, sir.
audible?
Yes, sir. Sir, any question from the audience?
Yeah.
So I'm sharing the slide again. Okay. Just
Yeah, it was a very nice presentation. It was a very nice presentation from the presenter.
Sir. Thank you, sir. Thank you, sir. Thank you. Sir, any question from audience? We can take it a couple of questions. Okay, then. Thank you, sir.
Yeah, first
Thank
of
you,
all,
sir.
we'll ask the audience if you have any questions. Okay. So I think we don't have any questions from the audience.
Thank you, sir. Sir, will ask us. Sir, any question from your side, sir?
Yeah, well, one question I will ask, how you found out this time complexity as the order of n?
Actually, sir, I think to build a dictionary, we have to, because we got a data set of English dictionary, so which is containing, so we are assuming that there are n number of sentences. So to build this dictionary, we have to scan every English sentence to find out the indices, because we have to build the indices for this dictionary. So to build indices, we have to scan through every sentence and find out which are the absentees list. So this makes it complexity as order of n, because the scanning of a sentence is constant time. It doesn't, because we assume that compared to the size of the data set, the size of the characters present in a sentence is constant. So it is like n into some constant. So making it we are we're saying that it is order of n. I hope we are correct.
that's all.
Are you calculating in one sequential order only? You are not calculating any repeatedly. Repeatedly, those values are not used.
No, sir. No sentence is repeated while building the dictionary. We are just scanning once, and the index is built, and accordingly, it has been set into its corresponding sub dictionary or sub value pair.
Okay, so thank you.
Thank you, sir.
Thank
Thank
you.
you very much.
Thank you. Yeah. Jason लिखते हैं.
Then we'll move to the next paper. The next paper ID is 76. Authors, are you ready?
Wait, my camera. Is it on now? Okay, it's on. I'm ready, sir.
Yeah, please start.
Okay. Is the screen already shared, sir?
Yeah, it is visible. Please start your presentation.
Okay, hello, glad to see you all. My name is Afik as the first author of this paper, and my coworker also, there's Mr. Aidil, Tuhari, and Mr. Dandi. And this is the presentation of the paper with the title Botnet Spam Activity Detection based on Network Traffic Analysis using Machine Learning Algorithm. The presentation consists of 4 sections. Those are introduction, the proposed method, experiment result, and the conclusion. First, we give an introduction about our topics, that is, about botnet. A botnet is a network of infected devices commonly referred to as bots. They are controlled by a central entity called a botmaster. These botnets are used for malicious activities such as distributing spam, launching DDoS attacks, and spreading malware. Spam, accounting for over 30% of network traffic in 2002, is particularly dangerous as it spread malware and facilitate formation of botnet networks. So, various detection models have been introduced in multiple approaches, such as machine learning, neural network, graph-based clustering, and a combination of various approaches with hybrid technique. However, the majority focus on binary classification, distinguish only between normal and botnet activities. The approach is limited when dealing with specific challenges like identifying spam botnet activity, which require a more sophisticated multi-class classification model. Recent research has advanced also about botnet detection through multi-class classification approach. Putra et al. Pioneered a two-stage detection system using stacked decision trees, first distinguishing between botnet activity from normal network traffic before identifying the spam attack. Meanwhile, Chunduri developed a robust IoT botnet classification using real-time traffic analysis with multi-level models, while Ashok enhanced detection capabilities by combining synthetic data generation with XGBoost to accurately identify 9 distinct IoT attack variations. Now, our research focused on addressing the challenge of botnet detection, specifically spam botnet. The goal is to build a multi-class classification model capable of distinguishing between normal activities, botnet non-spam activities, and botnet spam traffic. To achieve this, we employ a compare machine learning algorithm like decision tree, random forest, k-nearest neighbor, naive-bayes, and logistic regression. The next section is an explanation about the method we propose to achieve the goal of this research. Here is the architecture of our proposed method. We use sensor tree dataset from NCC2, which contain bidirectional network flow data for botnets. The process starts with pre-processing, including data labeling, encoding, and feature selection to prepare the dataset. After that, the data is split into training and testing sets to ensure balanced representation. And finally, we apply multiple classification algorithms to analyze the data and generate classification results. In the data preprocessing phase, we perform 3 key steps. There is the first data labeling. Network activities were categorized into 3 classes: normal, botnet non-spam, and botnet spam based on the label feature. This ensures distinct classification targets. And the next, for the encoding, the proto feature was one-hot encoded into 17 binary features as it plays a significant role in botnet detection, while other categorical features were excluded. And finally, in the feature selection, feature with high missing values were removed to enhance the dataset's reliability and improve model performance. And then on the data splitting, to handle the class imbalance, the data was split into 70% training and 30% testing, ensuring balanced representation of normal, botnet, non-spam, and spam data. Each category was split proportionally before being combined for balanced datasets. This method improved generalization and model performance. The classification is performed using machine learning algorithm. There are 5, namely decision tree, random forest, Gaussian knife Bayes, knife Bayes, logistic regression, and k-nearest neighbor. Okay, next section, we discuss the result of testing using Python programming language. So the tests are carried out using the NCC sensor tree dataset, only one dataset. This dataset was chosen because it effectively simulates botnet attack, including simultaneous botnet activity beyond spam, making it unique suited to the research objective. Although the reliance on a single dataset may introduce a potential challenge such as overfitting or limited generalizability. This table provides the detailed performance comparison of the 6 machine learning algorithms in detecting normal, botnet non-spam, and botnet spam activities. As you can see, the k-nearest neighbor algorithm stands out with the highest F1 scores across all categories specifically. It achieved F1 of 99.2% for normal detection and 90.21% for botnet non-spam, which highlight its ability to capture complex patterns in legitimate and malicious traffic. However, like most of the other models, KKN also struggle with botnet spam detection due to the class imbalance, achieving an F1 score of 70.56%, but still outperform the other algorithms. For instance, decision tree and random forest show better performance in normal traffic detection, but struggle significantly with botnet spam, achieving F1 score 69.36% and 60.06% respectively. Logistic regression and both knife-based models perform poorly in botnet detection due to their reliance on simplifying assumptions that fail with complex and nonlinear data. Next table focus on the overall performance metrics. That is macro average, with average, and the accuracy. So the k-nearest neighbor algorithm once again leads with the highest weighted average and an accuracy of 98.45%. This reflects its ability to handle multi-class detection effectively even with imbalanced datasets. The decision tree and random forest algorithm also achieve competitive accuracy scores of 97.04 and 96.71 respectively, but their macro average, particularly for recall and F1, are much lower due to performance in botnet spam detection. Gaussian knife Bayes struggle the most with accuracy, dropping as low as 3.22% for knife Bayes due to its assumption for feature independence and unusability for correlation numerical data. Logistic regression perform well for normal traffic detection, but fails entirely in botnet detection, as you can see in the previous table, confirming the need for more adaptive model like k-nearest neighbor. So finally, we come to the last part, which is the conclusion. So our conclusion is highlight the success of the 3-class model approach in detecting botnet spam attack. Among the various machine learning algorithm that is tested, the k-nearest neighbor algorithm stood out with remarkable performance metric, a weighted accuracy of 98.45, a precision of 98.41, and a recall of 98.45, and an F1 score of 98.4. This result demonstrates the robustness of the framework and its potential applicability to the real-world network environment, making it reliable, of course, for approach for addressing the botnet spam detection challenges. Looking ahead, our future work will focus on hyperparameter tuning to optimize the algorithm performance, and then to incorporate more diverse datasets to improve the generalizability of the model and also mitigate overfitting type risk. Additionally, refining the pre-processing pipeline will enhance the robustness and efficiency of our framework, ensuring more reliable detection of botnet activities. And this is the end of our presentation. Thank you. Is there any question? Okay, thank you.
Okay, sir. Let me share my screen. Can you see my screen, sir? Okay, thank you for the opportunity. Hello, good afternoon. It's great to meet you all. My name is Frederick Yunatan Susanto as the first author, and with the team Mr. Muhammad Aidil Rahman Putra, Mr. Tohari Ahmad, and Mr. Dandi Pramana Ursyadi. I'll be presenting our paper with title Enhancing Botnet Spam Detection through a robust assemble classification approach. This presentation is divided into 4 sections: an introduction, our proposed method, the experiment result, and finally the conclusion. First, we will provide an introduction to our topic covering botnets and assemble classification. A botnet is essentially a network of compromised devices, all controlled by a center figure known as a botmaster. This control is often maintained through a command and control or CNC cipher. Botnets are incredibly versatile tools for attackers, capable of launching DDoS attacks, sending spam emails, hosting phishing websites, or even stealing sensitive data. Now, focusing on spam botnets specifically, these are particularly dangerous because they can exploit multiple devices simultaneously for malicious activities. Now, about the research about botnet detection. First, there are signature-based detection. It involves predefined patterns in network traffic, while anomaly-based detection focuses on recognizing unusual behavior. DNS-based detection analyzes DNS traffic for botnet activity, and data mining techniques employ advanced frameworks to uncover hidden botnets. Now, there are research about botnet with assemble classification before. There are from Bijal1, botnet analyzing using assemble classifier, effectively combining multiple models to improve detection accuracy. This approach demonstrates the potential of assemble methods to enhance the identification of botnet activities by leveraging the strength of different classifiers. Next, in this research, we aim to create a model that can detect botnets by using a combination of machine learning algorithms. The goal is to separate normal network traffic, non-spam botnet traffic, and spam botnet traffic. We use several algorithms like decision tree, random forest, k-nearest neighbor or KNN, naive bias, and logistic regression to help improve the accuracy of our detection. The following section will describe the method we propose to achieve the objective of this research. This is the architecture of our proposed method. We utilize the sensor tree dataset from NCC2, which include bidirectional network flow data for botnets. The process begins with data preparation involving data labeling, encoding, and filter selection to ready to the dataset. Then the data is divided into training and testing, set to maintain a balanced representation. Finally, we applied assemble classification algorithms to analyze the data and produce classification result. In the data preparation, we did 3 main steps. First, we label the data into 3 categories: normal, botnet non-spam, and botnet spam, based on the label feature. Next, we use binary encoding on the photo feature, turning into 17 binary features, as it is important for botnet detection, and remove other categorical features. Finally, we remove features like DTOS and STOS that had many missing values to make the dataset more reliable and improve model performance.
Sorry, Mr. Frederick. I think
Yeah.
the screen is not shared properly. Maybe you can back to share the entire screen, maybe.
Oh, wait a minute.
Okay, it's
Can you
better
see
now.
the screen now?
Oh, yeah. Maybe it's not with presenter view.
Like this?
Yeah, okay. Thank you, Mr. Frederick.
Okay, we continue. Now to address class imbalance, we divided the data into 17 for training and 30% for testing, ensuring that normal, botnet non-spam, and botnet spam categories were even represented. Each class were proportionally split before merging to create balanced datasets. This approach helped improve the model generalization and performance. Now about machine learning classification algorithm. The classification process used several machine learning algorithms, including decision tree, random forest, logit segregation, naive bias, and Karenius neighbor. How about the experimental results? The section presents the experimental result testing by Python programming language. The test utilized the NCC2 sensor tree dataset chosen for the ability to simulate various botnet attacks, including those beyond spam. This makes the dataset highly relevant to our research goal. However, it's important to note that relying on a single presence can lead challenge such as overfitting and limited. Now this is the first table. From the table, we can provide a comprehensive performance comparison of 7 assemble classification combination in detecting normal activities, botnet, and botnet spam. Combination 5 demonstrates best overall performance, achieving an impressive A1 score of 99.51% of normal detection and 74.7 sorry 74.6.72 for botnet non-spam detection. This result underscore is effectiveness and distinguish between legitimate and malicious traffic, while the other combination also perform well on normal traffic. They consistently struggle with botnet spam, with F1 score ranging from 73.40% to 73.96%. Move to table 2. There are macro average and weighted average. The DT, RF, and KNN mean decision tree, random forest, and K-nearest neighbor assemble stand out as the power combination, delivering impressive result in precision, recursion, F1, and overall accuracy. The macro average metrics are particularly notable, with a precision at 92.91% and 86.70% and F1 at 89.55%. The weighted average metrics further highlight the assemble excellence. Next, the conclusion about this research. First, the assemble classification show that the assemble classification model is effective in detecting botnet spam attacks. And the second, the combination of decision tree, random forest, and Karenius neighbor algorithm with hard forwarding strategy effective balance design for accurate classification, with a data result weighted accuracy of 99.99% 99.05%, precision of 99.02%, and a recall of 99.05%. And the F1 score is 99.03%. So about the future works, we want to first improve the data preparation phase by addressing missing values and incorporating additional features. This will help us create a more comprehensive and reliable dataset for analysis. And the second, we analyze the assembled model for moment in various scenarios and compare it with other detection methods. This provides valuable insights into its strength and areas for improvement. And the last one, adapt the model to evolving threats and network conditions to maintain long-term effectiveness. So maybe it's all about our research. Thank you. I'm sorry if there are miscommunication. Thank you so much. Is there any question?
Thank you for your presentation. Is there any questions from the audience? Okay. So if no questions are there from the audience, I'll have some couple of questions I have. Like this botnet, we have a lot of botnet techniques, and you are telling that you are achieving some 98%, 99% precision recall F1 score. People have already achieved it. Whatever the machine learning algorithms you are using, are you thinking that this is not already used?
Maybe there are assembled classification for botnet detection before, but the accuracy not high as our team use. So we increase the accuracy, precision, and the recall for the assembled classification method. Maybe about the combination of the machine learning algorithms that we use to detect the botnet. Thank you.
There is no comparison with the existing work. Have you done any kind of comparison with the existing work?
In the existing one, include in our paper, sir. Wait.
Okay, thank you.
Thank you.
Can we have the next presenter? Who is the next presenter? Paper ID 25. Then paper ID 63.
Good afternoon. Am I audible?
Yeah, you are audible.
Yeah. I'll be sharing my screen. Okay. Is my screen visible?
Yes, it is visible. Please continue with your presentation.
Thank you, sir. A very good afternoon to everyone present here. I am Vedant Dotre with the Department of Information Technology of Somaya Vidya University, KJ Somaya College of Engineering. I am the first author for this paper, along with Sahana Ganesh, Pranav Patil, and Deepti Paude. Our research titled The Comparative Analysis of Cross-Lingual Neural Machine Translation Models is essentially a comparison between the different neural machine translation models that are present in today's world. We quickly go through the table of contents. We will be focusing on what machine translation is, the recent advancements in neural machine translation, the related work that we have studied, the architecture pipeline, and followed by the three main models, which are the LSTM sequence-to-sequence model, the transformer architecture, and the Google's MT5 model. So this paper essentially explores the recent advancements in machine translation, and it is primarily focused on Marathi to English. These are two Indic languages which we have focused for our study. So hence, we evaluate the various neural machine translation models, including the LSTM, transformer, and Google's MT5 model to understand the performance and limitations. So the challenges in Marathi to English translation are essentially the cultural and the linguistic nuances which affect the translation and the issues related with these low resource languages. There's also the problem of context preservation and long-term dependencies as we see in RNNs. So what is machine translation? It is the automatic translation of any written text while trying to preserve its meaning. And what this does is it enhances the connectivity and communication across languages. There are three main key machine translation approaches, which is the rule-based machine translation, which has some predefined rules, and hence, due to those rules, we lack flexibility in our approaches. There is statistical machine translation, which is highly data-driven, and it also struggles with context. And finally, neural machine translation, which is the basis for our study in this paper, which leverages neural networks for higher accuracy and fluency. So the advancements in neural machine translation are as follows. There is an encoder-decoder framework introduced with RNNs, which is effective but struggles with long-term dependencies. The LSTM networks address these limitations posed by the RNNs, but have also a significant loss of information in the fixed dimension vector mapping. And followed by the attention mechanism, which is the one of the recent advancements, which focuses on the relevant inputs given to it, and hence improves the translation accuracy overall. So coming to the transformer model, which employs this attention mechanism, it overcomes the RNN's limitations, and some of the key features include the self-attention mechanism. It ensures parallel processing for higher efficiency and speed, and also is the foundation of the modern NMT systems. So hence this sets the benchmarks for the translation tasks. We have gone through some related work in this field. We have gone through work published by Sahana Ganesh et al. And this talks about the challenges that the RNNs possess, mainly being the long-term dependency problem in translating longer sentences. This is mitigated by adopting LSTM models and other attention models as well. And essentially, it improves the translation accuracy. Transformer models, of course, they outperform traditional models like PBSMT, which is described by another researcher in the same field. This is outperformed in terms of short sentences and fluency. Akshay Ramesh et al. Proposed the PBSMT model, which is still an effective model for longer sentences and mainly complex terminologies. So this is mainly used in morphologically rich languages. Moving on, we also see a focus on the low resource languages, mainly English to Tamil, which was focused by the same researcher Akshay Banerjee et al. And this focus is on the transfer learning using multilingual NMT models, and it uses a pivot-based method to improve translation. Now, attention-based sequence-to-sequence model. Nikuj Bansal et al. Proposed this model of constantly outperforms the LSTM model, particularly for longer sentences and complex structures. And of course, there's some future research that has been conducted by Himanshu Chaudhary et al., which talks about the transformer models and how integrating transfer learning to address these low resource languages is shown as the future of NMT. This is the pipeline that we have considered for our study. We start with the raw corpus for Marathi to English translation. Then we generate a vocabulary based on this corpus, followed by some pre-processing such as tokenization and padding of tokens such as the EOS, end of sentence, start of sentence, and other tokens that we need. Followed by the three main models of our study. The transformer model, which is as shown in Vaswani et al. Attention is all you need paper. This consists of an encoder and a decoder. Then the LSTM model. And finally, the MT5, which is fine-tuned or using transfer learning to focus primarily on this task of Marathi to English translation. Followed by which we evaluate and compare the outputs based on the blue scores. Coming to the LSTM sequence-to-sequence model, these are essentially specialized RNNs, as we discussed before, and they address the long-term dependency, the vanishing gradient problem of RNNs. Hence, it retains those dependencies in sequence, and that is what makes it superior to the traditional RNNs and hidden Markov models for sequence learning. This is also utilized in machine translation with an encoder-decoder architecture. Moving on, we go to the transformer architecture. This is, as discussed, based on the proposed architecture by Vaswani et al. It leverages self-attention within the encoder to process input sequences efficiently, and it overcomes the drawbacks as stated in the RNN LSTM by processing the input tokens simultaneously. Due to the parallel processing feature of transformers, we get better results and better translation accuracy. Some key features are the positional encoding. This adds the information of the position of the input embeddings with respect to other inputs. And also the multi-head attention. It performs the attention mechanism in parallel to attend to multiple different positions simultaneously. This helps in capturing the dependency of those words. Followed by the Google MT5 model. Single model, which is pre-trained on a common crawl data set of 101 languages. We have further fine-tuned it on parallel sentence pairs for English to Marathi translation. The training details is as follows. We've used the RMW optimizer with a linear scheduler, a batch size of 64, and this was trained on the NVIDIA Tesla T4, which is 16 GB VRAM. We have also used the Hugging Face transformer for training the MT5 model. Here is the brief overview of the algorithm that we have considered. It mainly includes tokenization and encoding, which is part of the pre-processing, followed by the translation, which is generated from the trained model. And after that, post-processing of any tokens to be removed or any other unwanted results. So moving on, we come to the results and analysis. We have utilized the Blue 4 for determining our results in the context of translation. Now, when it comes to Marathi to English translation, the transformer architecture, which we trained using Python and the proposed architecture according to Vaswani et al., we came across the blue score of 0.39, which is the highest out of the other three. This served as a benchmark for us to even try translating any a further low resource language pair, such as Tamil to Hindi, and we achieved a blue score of 0.4, which is very great. So as you can see, the transformer consistently outperformed in terms of the contextual understanding and the structure of the sentences. This was done by a qualitative analysis of the results that we had obtained, which included moving across different domains such as lexical choices in the translation of the named entities, any idiomatic phrases which had some context to be preserved, along with any non-literal phrases as well. Of course, there was a challenge which remained, which was preserving the context and handling low-frequency words. we encountered a few unknown words which are not present in the vocabulary as well. So finally, to conclude, the transformer model gave us a blue score of 0.39 in terms of Marathi to English translation, along with 0.4 in a further low resource language pair of Tamil to Hindi. Now, what this does is it highlights the transformer's ability to handle the structure and relationship across different languages. The MT5 model, of course, it is the same architecture, but it was fine-tuned for Marathi to English. It had promising results overall, but it underperformed in the specific tasks I discussed before for the qualitative analysis. This signaled a need for some empirical evaluation and language-specific tuning. So, further difficulties in preserving the context and translating those low-frequency words emphasizes the need for some better model designs and training approaches. And of course, there is some potential for cross-lingual communication, enhancing that potential, and some cultural exchange through the improved translation quality. The future directions of NMT. So, in terms of where the future is headed for NMT, we can also look at human feedback integration. I think this is particularly important when we are considering low resource language pairs where we do not have enough or adequate information or data to train models for more adequacy, right? So this is certainly something which is important. Utilization of generative models when we consider only monolingual corporas, right? Where we have only one particular language pair, such as maybe we take example of Tamil to Hindi. We only have data for Tamil. Utilization of these generative models for enhancing the low resource language translation can be very helpful. And as discussed before, there should be a focus on the empirical evaluations and more language specific model tuning. These were the references that were considered for the study. Thank you.
Yeah, Mr. Vedant, that was a nice presentation.
Thank you, sir.
So in this model, you have used only transformer model.
No, sir. So this was essentially a comparison between the three different models, right? The LSTM based model, which is the encoder decoder based model, followed by the transformer architecture model. And we use the MT5 model as a benchmark to compare the outputs of all three and evaluate our results.
You have used one of the performance metrics like blue score. What is that?
Yes. So blue score is essentially, well, it stands for the bilingual evaluation understudy score. So it is basically a metric used to evaluate text generation. And it's more so used in machine translation, which is the basis of our study. And so it's based on some n-gram matching. And what it does is it uses those n words, a contiguous sequence of n words. Maybe suppose we consider 2 n-gram, right? Here in the study was 4 n-gram. So 2 n-gram, if we consider, which would be bigrams. So a sequence of 2 words or 2 contiguous words are used. And this is then, if I go to this, right? So there's a concept of brevity penalty and an n-gram overlap. So that n-gram overlap of those n words is used to understand the or to evaluate the blue score of the text generated for that sentence.
So this blue score you have calculated for LSTM as well as for transformer.
Yes, for LSTM, for MT5, and for the transformer.
Okay, so thank you for your presentation.
Thank you, sir. Thank you so much. Thank you for everyone to listen to presentation. Yeah.
Yeah, we'll move on to the next presenter. I think only one paper is left. Paper ID 25. Paper ID 25, the authors are present here. No, I think they are not present here. Okay, so now it is over to the organizers. Should I conclude the session here?
Okay, thank you, Dr. Tripathi, for chairing the session. So with that, we conclude the session as well as the conference here. Unfortunately, 2 or 3 authors could not able to present. Maybe we need to reach out to them for that. Thank you all participants for your support and your patience, and all the session chairs and guests for your participation. And we look forward your participation again next year. Thank you. Happy New Year to everyone.
Thank you, sir.
Thank you, sir. Happy New Year.
Happy New Year.